Hello, welcome back. We are in the topic of binary search trees or BST, and this lecture we are interested in how to insert an element into a binary search tree. Okay, so let's say I have a binary search tree. Here is an example on the board, and now I want to insert a new number into this tree. Let me say I want to insert the number 60. Okay, I want to insert 60 into this binary search tree. So where do you think I should insert? What should I do to insert this? Okay, I will do the following, right? I start from here. So, okay, so here is the idea. So what I'm going to do is that I'm going to follow the same procedure just like I used to search for an element, right? When I used to search for an element, so the same idea I'm going to use now. I'm going to keep searching for the number 60, and when I see that, when I reach a point where 60 is not present there, when I see that, I'm going to insert the number 60 at that position. So let's go through this example. So I come here, right? I am looking for 60. I come here. I reach there. I turn 60 is less than 100, so I turn left, right? And then 60 is greater than 50, so I come here, and now I am here, and I am in 80, and I see that 60 is less than 80, and I go there. So I come here and I realize that okay, it's null. I can't go. There's nothing to go this side. So what do? I insert 60 here, right? Okay. Is it clear? So now let's say I already inserted 60, and now I want to insert another number. Let's say I want to insert 70. On top of this, what happens? Again, I start from here. 100, 70 should go turn left. Okay, turn right because 70 is greater than 50. Turn left because 80 is greater than 70. Now I'm in 60 and I'm looking for 70. I have to turn right, and so I put right. So this is binary search tree. Is it clear? What about inserting 250? What do? 100, 200, 250. So this is insert, right? And what about 110, 100, 200? So 110 is greater than 100. So you come here. 200 is greater than 110. So you turn left. 110 is less than 150. So I come here and I put. So clear? Okay. So good. So now we know how to insert an element into a binary search tree. Let me write the function for this. Okay, and I'm going to take a root. Okay, and the number to be inserted. So this key has to be inserted into this BST, and what happens here? First thing to do is the following, right? I have to check whether I'm going to check whether I have to turn left or right. Okay, so let's first do that check. I do the following. So I do. Okay. So t dot key is, let's say, is greater than key. Right, so I'm in 100 and it's 100. Let's say I'm going to insert 40. So t dot key is greater than key 40, and therefore I have to turn left. So once this is the case, I have to do the following. I have to check whether, I have to do two checks. I have to see whether this is left is equal to null. Now, if this is equal to null, what does it mean? Right? If this is equal to null, it means that see, if this is equal to null, it means that, right, I have kind of reached the end, right? I've reached the end and there is nothing, there's no more element to traverse in this left direction. So in that case, I'm going to insert that element there. So I'm going to say that t dot. So I'll create a new node. Okay, so t dot left equal to new node, and I pass the value key. Right, so this basically creates a new node with the key value there, and that's it, and then I return. Okay. On the other hand, if t dot key is greater than, if t left is not equal to null, so an else here. Okay, so this is this. Sorry, this is this, and if t dot left is not equal to null, what should I do? I go left. I turn left, right? So I insert. I go left and I insert there. That's it. Okay. So this is if t dot key is greater than key, and there's this extra condition on. I mean, you also have to write for t dot keys. So okay, I'm not going to write, but we'll just show, and then you can fill this thing up. What should you do in this case? You will have to turn right. And so here we had inserted it into the left. On the other hand, here you will have to insert on the right. This is how you will create a binary search tree. Also, I didn't take care of certain things. For example, if the tree is null, there is no element in the tree, you have to insert this key. So you have to, that's not taken care of here because I am assuming that this root has some value here. I mean, that's already there is a node in this tree. Now, so we have to take care of these things, right? So if the tree is null, you will have to also create a new node and make the node as a root, etc. So those, that's not part of this code right now. Okay, now, but you get the idea of how this has to be done. Okay, now going forward, let me give you a sequence of numbers and let's build together a binary search tree, right? Okay. Okay, so the numbers are, I'm just going to randomly write some numbers, 70, 50, 110, 80, 30, 10, 90. Okay, let's see. I'm going to insert these numbers in sequence. So right now, there's no element in the tree. So I'm going to first insert this number 70. So 70 comes here. Okay. Then 50 needs to be inserted. I come here and I put it on the left. 110 comes here, so I come here and I put here. 80 comes here, I come here. 80 is great, so I come here, and 80 has to be less, right? So 80 goes there. 30 comes here, 50, 30 has to go there. 10, 70, 50, 30, 10. 90, 70, 110, 80, 90. Okay. So this is my binary search tree for these numbers. Okay, if you had 60 here, okay, so 70, 50, 60. Right? Okay, 150. Right, so this is how you insert numbers into the binary search tree. Here comes the question. I give you let me give you a different sequence. Okay, and again, let's try to build the binary search tree for it. Let me give the following sequence. And so I'm going to insert 100 first. So 100 comes here. 90 is inserted next. 90 comes to the left. 80 is next. 80 comes to the left. 70 comes to the left. Okay. You get the picture what is happening, right? This is not a good binary tree, right? This is a path which we had. This is not a good binary tree. Why is this not a good binary tree? Because if I get a binary tree like this, and let's say I'm going to search for the number 50. What happens? I have to go through the all the numbers in this list, and that's not good. That takes if there are n numbers, that takes me n searches, right? I have to do n comparisons to comparison in the sense I have to do an if check, right? I have to visit all of these n nodes to find the number 50, right? Okay. So on the other hand, this tree is fine, right? Because this tree is fine. Why is it fine? Because I don't have to go through all the nodes. If I want to search for the number 60, I just have to visit 3 nodes to get 60, or a number 90, and I just have to visit 4 nodes to get this number 90. But I have a lot of other nodes too. So this is a bad tree, and these trees are called as skewed trees. Okay, this is the word skew. Okay, it means basically the tree looks like this. It's not a balanced tree. So these trees, or a complete binary tree, is called as balanced trees. Right? Okay. So we are interested in balanced trees, because if it is a balanced tree, then it means I don't have to go through all the nodes to when I'm searching for a number. On the other hand, if it's a skewed tree, I have to visit all the nodes when I'm searching, and that's not good, right? Because that we already saw that this takes a lot of time and this takes less time. And we are interested in balanced trees, but as we see here, this inserting in a binary search tree might produce skewed trees, which are not good for us. When is it? Why is this a skewed tree? What kind of input will create a skewed tree? Can you see from this list of input? Can you see what kind of input this is? You can see this is a numbers in a descending order, right? If I have a descending order, if the numbers are in descending order, then you get a skewed tree, right? What about if the numbers are in ascending order, 50, 60, 70, 80, 90, 100, you insert like that, then also you get a skewed tree. How will it look like? It's going to look like this. A path which goes right. This is a path which goes left. That other one is called going right. That's also a skewed tree. So skewed trees are not good because it's going to take a lot of time. We want balanced trees. Okay. Right. Another question. So before we see how to, this is a question which we will always have to think. What do we do to balance a binary tree, right? So we will, I will, okay. So if you are, now if you want a balanced binary tree, you have to look at what are called as Avl trees. So there are multiple binary search trees which balances the tree, which creates balanced binary trees, and those are called as few examples are Avl trees, okay, red black trees. These are a few examples of balanced binary search trees, and so in those trees, it's not an insert like this. Okay, it involves certain other procedures to ensure that the tree gets balanced. Such a tree, a skewed tree, does not appear in trees like Avl trees or red black trees. So they use certain other. The insert function is a little more complicated. They do things which are like so they change the structure of this tree once they insert a number. They're going to change the structure and make it into more balanced structure, and for that red black tree uses they color the vertices of the tree using red and black color. For doing that purpose, Avl trees maintain a number to do these things, etc., to create this balance. So it's a little more advanced data structure. Those are also binary search trees, but advanced binary search trees. Okay, and we will skip Avl trees and black trees. If you're interested, you can just take a look. It's probably it's there in all the books, LRS, Corman, or like any data structures book. You will probably find these things, or just Google. You'll be able to see Avl trees and red black trees. Right now, so this is clear. Now, so I want to ask another question before we end with binary search trees. There's just one more question I want to ask. We saw how to search for a number in a binary search tree. We saw how to insert a number into a binary search tree. But I ask you another question. I want to delete a number from the binary search tree. Okay, that's my next question. How do I delete a number from the binary search tree? So we're going to look at this tree. Okay, we look at this tree and decide we start deleting numbers, and I will see what needs to be done. Okay, let's first look at the easy case to delete. I want to delete or remove. Let me call it remove. I want to remove 10. Okay, where is 10? Here. I want to remove 10 from this binary search tree. How do I do that? It's very easy, right? I just come here and I go to 30 and I just remove this, right? Okay, so remove 10 means I just start searching for 10, 10, 10, 10, and I reach there, right? Once I reach there, I just remove from the parent. So why was that easy? Because this is a leaf node, right? So removing a leaf node is easy. So this is something you can. So removing just remove that, okay, and put null to its left pointer. Okay, just put null for 30's left pointer, and you have done. It's as easy as that. Okay, now let's look at something complicated. I want to remove, let's say, 50. Okay, now it's not a leaf node. Okay, so if I want to remove 50, what should I remove? Okay, now, if I want to remove 50, what should I do? Okay, now, so, I can't just remove 50 like that, right? Because if I just remove 50 like that, it's not, I mean, there's a hole there, there's a gap. So I can't just remove 50 like that. But here is the idea. What I'm going to do is that, so I am interested in remove 50. What we do is we find out the successor of 50 in this tree. Okay, so what do I mean by successor of 50? The successor of this number is a number greater than 50. Okay, look at all the numbers greater than 50 and take the smallest among them. Okay, so successor is smallest number greater than 50. That is a successor. So successor of 50 is the smallest number greater than 50. In this tree, what is the, so like if you have natural numbers, what is the successor of number 50? 51, right? Look at all the numbers greater than 50 and take the smallest number. So 51. That's successor in natural numbers. But what about successor in this tree? So where are the greater numbers of 50 going to lie? It's on the right child of 50. Okay, so note that it need not just be that. Okay, it need not be the case. There can, things can be above also. Okay, those are also numbers greater than 50. But what we are going to do is that we are going to traverse here. Okay, and I'm going to find out the number smallest here. Okay, now, okay, so let me say a successor of 50 in the right subtree. Okay, in right subtree of 50. Okay, now, so that is the number 60. Now what I do is the following. I remove that number 60 from this tree. Okay. I'll call this number, I'll call the same function again, and I call remove 60. Okay, maybe that also has to be recursively removed. Right? Maybe 60 has its own children, etc. So then it will have to be recursively removed. But you find this, you remove that number, and then, so in this case, you can just remove it like this, right? You just remove it like this, and so 60 is removed, and then you just replace 60 here. Okay, so that is successor of 50 in the right subtree of this thing is removed. Okay, it's good. What about, let's we skipped a lot of special cases here. Let's consider again here. I want to remove number 60. Now remove 60. What should I do if I have to remove 60? Again, let's do this. Successor of 50. Oh, but there is no successor of 60 in the right subtree because 60 does not have a right child. Okay. In that case, what I can do is, so if there is only one node, and if a node has only one child, it's easy to do. Just remove this and connect this. Okay, so this is also easy. So if there is only one node, it's again easy. So removing leaf node is easy. Removing one child node is easy. Just remove that and connect it. Okay. Now it does not matter whether it's a left child or a right child. Just remove that node and connect its child to the parent. So remove one child node is also easy. Let's look again. This I want to remove the number 70. What is 70? 70 is the root. Right. I have to find out the successor of 70. Where is the successor of 70? Successor of 70 is this 80 in this right child. So you have to. So now you should tell me, how did I find out the successor? It's very easy to find the successor. So there is an algorithm to find successor, and it's very easy. What you have to do is you have to turn right. Okay, because as we said, successor on the right subtree is what we are interested in. You turn right, and then you just go on left side. Okay, so that there you will find the smallest number in this left in this binary search tree, in this left tree. So the smallest number in a binary search tree is always found on the leftmost point. So the smallest number in this subtree is found here on its leftmost. You keep on going left and you reach this 80. Okay, so you have found out the successor of 80. What do you do now? Just right, you remove this 80. How will you remove this 80? You have to do the same thing. What is the successor? So if you want to remove 80, what is its successor? Okay, so you first, let's say you do the following. You are going to replace this root by that successor number, and then you are going to remove this 80. And if you want to remove this node, what will happen? You have to find its successor. Found its successor here and replace this. Right? Is it clear? Okay. That's how you're going to do this. Right. This is the algorithm for removing an element from the binary search tree. And okay, so like how do you write an algorithm? You have to first write the base case for this. The base case is remove leaf node. If you find out and you found and you searched and you reached the base case of leaf node, just easily remove it. Or another base case is it's a one child node. So that node has only one child. So if a node has one child or zero child it's a leaf. Both cases it's easy. If it's zero child, you just remove it. One child, you just remove it and connect its child to its parent. So those two are the easier cases. On the other hand, if neither of them, so that means a node has both left and right nodes. Okay, so if a node has both left and right node, you find out its successor element in its right subtree, and recursively you remove that and then replace it here. Okay, that's what we did here. This is how you will approach a this is how you're going to remove a number from a binary search tree. Now here is a question. You could have also did the following. Here I found out the successor, but you could have even removed the predecessor. Okay, predecessor is basically the number which is the largest number smaller than here it's 50. Predecessor of 50 will be, so in natural numbers predecessor of 50 is 49. Okay, largest number smaller than 50, 49. On the other hand here, if you had to, what is the predecessor of 110? On its left subtree, 110's predecessor is 90. Okay, right. So let me, if this was the tree, let's say 95. This is 80, so 85. Okay, if this was the tree, what is the predecessor of 110? 85. Okay, sorry, it's 95. I'm sorry, I made a mistake. You turn left and then you keep on going right. Then you get this. This is the predecessor of 110. Okay, largest number less than 110 is 95. So you turn left and then you keep on going like this. That's how you're going to get predecessor. How did you get successor? You turn right and then keep on going left. Okay, so you get predecessor and successor like this, and this is good. Okay, so now we have seen how to insert or delete, remove an element from a binary search tree, and we finish our topic on search trees. One catch, maybe I never mentioned this, but probably while we are doing this, we might have seen this. that in all these things we are assuming that there is only one, there's only one number, okay, sorry, the numbers are distinct. So in a binary search tree, the numbers have to be distinct. What do I mean? In a tree, there is no two occurrence of the number 80. 80 appears only once, okay, 90 appears only once, 110 appears only once. So the numbers have to be distinct in a binary search tree. In search trees, so to conclude, in search trees, the numbers, the key values have to be distinct, right? So that's how a dictionary, the value, the keys are distinct in a dictionary, right? Okay, now and this brings to an end our lectures on search trees. We have seen binary search trees, and I also gave a hint on other advanced search trees like Avl trees or red black trees. Thank you.